Hi, my name is Dr. Izzy Goodman, and I'm here in the Chemistry 101 lab at Pierce College. And what I'm going to do today is carry out Experiment 2, which is Chemicals in Everyday Life. It's a series of tests, 8 different tests involving some common chemicals that you encounter in your everyday life. And you'll prepare your lab notebook as it's described in the experiment by dividing 5 different pages in your lab book into 3 different columns labeled procedures, observations, and conclusions. You'll fill out and outline form the procedure column, and then you'll be prepared to watch the video. But before we start, of course, we must put on our safety goggles. All right, now we're protected. So in part 1 of this experiment, we're going to carry out tests for chloride ion and sulfate ion. So first, the procedure calls for preparing some 3 molar nitric acid from 6 molar nitric acid. And so using M1V1 equals M2V2, we're going to use equal volumes of nitric acid and deionized water to go from 6 to 3 molar. We don't need much, so I'm just going to add 5 drops of the nitric acid, and then follow that by adding 5 drops of deionized water. Mix that up, and there's our approximately 3 molar nitric acid. Okay, so now we're going to take a small amount of Epsom salts, and Epsom salts you can purchase in any drugstore. They are composed of magnesium sulfate heptahydrate. See if you can write the formula for that, recall the formula for that. We're going to take a small amount. You can see it's a white powder, and I'm going to put that in a test tube. Okay, and then I'm going to add approximately 1 milliliter of water. This is a qualitative experiment, so quantities are not that important, but we'll put in enough water to dissolve those Epsom salts. And there you go, you can see that forms a nice solution. And then we're going to take 1 drop of the 3 molar nitric acid that we prepared a little while ago and add that. And as it says in your procedure, the nitric acid is not involved in the reaction. And then as a last step, we're going to take some 0.2 molar barium chloride solution and add 1 or 2 drops to that. And you make your observations. Okay, I'm going to set that aside for 10 minutes and we'll come back to it. So this is what it looks like after about 10 minutes. And you can see that all the precipitate has settled to the bottom. And now I'm going to pour off the liquid above it, it's also called the supernatant, into another test tube. This process is called decanting, is the chemical term for that. Okay, so we've left the precipitate behind, and now we have the solution above. And to that, I'm going to add about 1 to 2 milliliters of the 0.1 molar silver nitrate solution. And you can make your observations. Okay, so now on to the first part of part 2. And I'm going to light my Bunsen burner first. And we're doing this part in the hood. And I'm going to take some a magnesium strip out of this jar. And this is what our magnesium strip looks like. Okay. And I'm going to put that magnesium strip into the flame. So make your observation. And what you can see, what we have left is kind of a white ash. And I'm going to put that white ash into this beaker. Okay. So there's our white ash from the first reaction. And to that, I'm going to add about 2 milliliters of deionized water. And swirl that around. Some of it would dissolve, but not all of it. And then to that, I'm going to add a drop of phenolphthalein. And you recall phenolphthalein is a pH or acid-base indicator. And I'm going to add 1 or 2 drops to that. and make your observation. Do you recall phenolphthalein turns pink in a basic solution, but is colorless in a neutral or acidic solution? Now to the beaker, I'm going to add a few drops. I chose 6 molar HCl, hydrochloric acid, and swirl that, and you can see what happened. All of a sudden we're colorless. Okay, on to part 3, which is called tests for carbonate ion. The substance we're going to test in part 3 is chalk. And if you recall, chalk was used to write on blackboards. I guess I'm dating myself, if you don't remember that. And so we've ground up a piece of chalk here in this mortar and pestle. And I'm going to take a small amount of that chalk and add it to each of these test tubes. Okay, happens to be yellow chalk. And to one of these test tubes, I'm going to add 6 molar HCl. And to the other test tube, I'm going to add some common household vinegar. And there are the reactions, and you can contrast the speed of those two reactions. The second chemical we're going to test in part 3 is an antacid. In this case, Tums, berry flavored, and we've put some Tums in a mortar and pestle and ground it up, and I've taken samples of those two and put it into each of these two test tubes. And now to the first one, I'm going to again add HCl. To the first one, hydrochloric acid, and you observe what happens. And to the other, I'm going to add vinegar. And there are the two reactions. Again, contrast the speed at which those two reactions occurred. The last substance we're going to test in part 3 is baking soda, used for cleaning and deodorizing. In this case, Arm & Hammer brand, trusted brand. And I've put it in the two test tubes again. To the left one, I will add hydrochloric acid. And to the right one, I will add vinegar. Record your observations, and again compare the speed of the two reactions. Okay, on to part 4, which is a test for iron 3 ion. And you recall that iron exists in two stable ionic forms, iron 2, also known as ferrous ion, and iron 3, known as ferric ion. And we will use these tests to distinguish between the two. I'm going to start with some 0.1 molar solution of iron 3 chloride, and you notice it's got a slight yellow color to it due to the iron 3 ion. And I put a 0.5 milliliter of that solution in this beaker right here, and it says to dilute it up to 20 times its volume with deionized water, and so I've got about 19.5 milliliters of deionized water in this graduated cylinder, and I'm going to add that to the iron 3 ion solution. Notice it looks pretty colorless now because of the dilution. And to that solution, we're going to add 0.1 molar ammonium thiocyanate solution, and you observe what happens. Now notice what we formed here is not really a precipitate. It's really something called a soluble complex ion. In this case, it's called thiocyanate iron 3 ion. what I'm going to do is I've taken 1/2 milliliter of that and put it in this beaker, and I'm just going to dilute that up to 20 times its volume again. And what you can see is it is now almost colorless. So dilution does affect the strength of the color of a solution. Now for number 2 of part 4, we're going to take some iron filings. And iron filings are just a powder form of iron. You can see it's a very, very fine powder. I'm going to take a small amount of that and place it in this test tube. Okay. And to that, I am going to add a few drops of 6 molar nitric acid. All right, so make your observations. And again, these reactions in part 4 of this experiment, you're not going to need to write chemical reactions for because they're rather complex. So nitric acid actually oxidizes the elemental iron, the iron that we started with. And now the question is, did it form iron 2 or iron 3 ion? So this is what it looks like after a few minutes of reaction. And you notice there's still some unreacted iron powder on the bottom of this test tube. And what I'm going to do is pour off some of that solution, or decant as the term, we learned the term earlier, some of that solution to get rid of the iron powder. Now we have this solution, and to this solution I'm going to add ammonium thiocyanate again to see whether or not we formed iron 2 or iron 3. And you'll notice we get that dark red, sometimes it's called blood red color. So what does that tell us? Your observation, what's your conclusion based on this observation? Okay, so on to part 4, number 3. And in this case, we're going to test an iron tablet, an iron supplement. These are obtained from Walgreens, and they're green tablets. And I put several in this mortar and pestle and ground them up into a powder. And I'm going to put some of that powder into a test tube. So I've added a small amount of the ground up iron pill to each of these 2 test tubes. And then I'm going to set aside one, and to the other I'm going to add about 3 milliliters of water. And mix that up. And then to that I'm going to add the ammonium thiocyanate solution again. And mix. And you can observe not much of a change. So now I'm going to take the other test tube, and to this test tube I'm going to add about 1 milliliter of water just to dissolve it. And then I'm going to add some nitric acid. And I'm going to let that react for a couple of minutes. So this is the second tube, the one that we had the iron pill in, and we added a bit of water and then some nitric acid. And we didn't really see much happening here, okay? No obvious sign of a reaction. But now let's test this using ammonium thiocyanate again. what do you observe? We got that blood red color again. And what did that tell us? Or what does that tell us as a conclusion? What did the nitric acid do to the iron pill? What form of iron was in the original iron pill? Okay, so we're up to part 5, which is the test for chlorine. And for this experiment, we're going to use Clorox bleach. Bleach is sodium hypochlorite, but it behaves as if it has chlorine gas dissolved in it. So the actual reactant for this reaction will be Cl2 gas. And in this test tube, I have a small amount of sodium iodide, which is as you can see, it's sort of a white crystal. And to that, I'm going to add some water. And mix it to dissolve it. Now to that sodium iodide solution, I'm going to add a few drops of the bleach. And you can see against that white background, it's turned sort of a reddish orange color. And iodine, solid, when it's dissolved in water, gives a reddish orange color. So what does that tell you about the product that was formed in this reaction? In number 2 of part 5, I'm going to use some iodized salt, sodium chloride, the kind you have on your table at home and use in your food. And I'm going to take a small amount. This happens to be an iodized form of sodium chloride. And I'm going to put a small amount of that in this test tube. And then I'm going to add some water again to dissolve it. And now I'm going to add a few drops of bleach again to this test tube and mix. Do you notice anything that happened? Why not? Okay, so we're up to part 6, which is a test for zinc. And for that, we're going to use a good old-fashioned American penny, as long as it's dated later than 1982, and this one happens to be 2017. And what you'll notice if you look carefully is that I've rubbed off the copper on the edge around this penny, and I've put a couple of nicks in the penny as well, okay? And what it exposes is a silver color. And what I'm going to do with that penny is put it in a beaker and add some hydrochloric acid. So now I've got my penny and I've come over to the top loading balance. And first I'm going to zero it. All right, and then I'm going to weigh my penny before I start the reaction. And this is going to be your data point 1, the mass of the cleaned penny. Okay, so there's my penny in the beaker, and here's my hydrochloric acid. And I'm going to add it to that beaker. And I'm going to cover it with hydrochloric acid. And you can already see something happening. And I'm going to set this aside for several days. Okay, so we're back with the postscript for part 6, where we're testing for zinc. And you recall that we took a penny, rubbed the edges of it off, and put it in several milliliters of hydrochloric acid. And here's what we have left currently. And you can see there's actually 2 little things floating in there. There's one, there's another. I'm gonna pour out the excess HCl, which you can see is pretty clear. So whatever reacted seemed to have dissolved. And then I'm gonna rinse it with some deionized water to get the rest of the acid off. And then we'll take a look at what we've got. Looks like we've got one very thin piece of copper and another very thin piece of copper. In fact, it's hard to tell which is heads and which is tails. And so I'm going to put them on this paper towel and dry them off. And as you can see, they're very flimsy. That's all that's left of our penny. Now, I don't know if you can see, but this looks like the heads part of the penny. It's maybe very hard to see on this video. And this one, if I look very carefully, is the tails part of the penny, which again, you may not be able to see. All right, I'm gonna go take these over to the top loading balance and weigh them. So here we are at the top loading balance, and I'm going to turn it on. And in order not to contaminate the top of the balance by putting a chemical directly on it, I'm going to use a piece of weighing paper, and I'm going to tear it so that the weighing paper is eliminated from the weight. All right, and now I'm going to take my 2 pieces of thin copper and put them on the balance. This will be your data point 2. So now, according to your lab book, you're going to calculate the percent of the penny that reacted and compare that to what you look up on the internet at the US Mint. The waste disposal fume hood in the Chem 101 lab, which is where I dispose of all the waste, and students would typically do this after each part of the experiment into the proper waste container according to their lab manual. So now we're over here in the fume hood, which is a location in the lab where there's a fan on the top of this enclosed area, which sucks air out of this area, removing any noxious fumes so that they don't go into the lab. They go out a stack that's a very tall stack on the top of the building. This happens to be our waste disposal hood, and in this waste disposal hood we've got 3 different common waste disposal containers: aqueous metal wastes, acid waste, and base waste. So any pure acid would go in the acid waste, any pure base would go in the base waste, and anything that has metal ions, toxic metal ions, would go into the aqueous metal waste. And if you'll notice in your lab book, after each of the tests, it indicates where to dispose of the various materials. And so this is the acid solution that was produced after the reaction of the penny, and it says to dispose that in the aqueous metal wastes. So I will do that. I still have all the rest of the test tubes that I used for this experiment. Most of them are going to go into the aqueous metal waste, so I will pour them in and rinse some of these materials. The acid and the base waste are both neutralized in our stockroom, and when they're neutral they can be poured down the drain as long as they don't contain any toxic metals. The aqueous metal waste, which contains the toxic metals, is collected in our stockroom over the course of a year and picked up by a waste disposal company that disposes of the materials properly. Okay, so we've reached part 7, entitled Testing for Relative Acidity. And what I have here are 4 liquids. Liquids you're familiar with: vinegar, again, some lime juice, 7-Up, and apple juice. And what I did is I put exactly 1 milliliter of each of those liquids in each of these tubes, then added to them a drop of phenolphthalein, the acid-base indicator we used earlier. Okay? And as you can see, they're all relatively colorless. Okay? So what does that tell you about these solutions? Remembering what phenolphthalein tells you, well, they're either neutral or acidic. And now what we're going to do is we're going to compare the relative acidity of each of these solutions by adding 1 molar sodium hydroxide to each until we see a color change. Okay, so here's my 1 molar sodium hydroxide, and what I'm going to do, starting with the vinegar, is I'm going to add the sodium hydroxide drop-wise to each of the tubes until I see a color change. And I'm going to slightly mix after each drop. So you can count with me. There's 1, 2, 3, 14, 15. There we go. Turn pink. That's your observation. What's your conclusion? Okay, So let's go on to our next tube, which is the lime juice. Okay, so let's count with the lime juice. There's 1, 2, 3, 13, 14, 15. There we go. 15 drops it took for the lime juice to turn pink. All right, let's go with our next one. And this one is our 7-Up. 1. Oh, that didn't take long. 1 drop for the 7-Up. And let's go to our last tube, which contains the apple juice. 1, 2, 2 drops. So 2 drops for our apple juice to turn it pink. So now follow your instructions, make a chart, and compare the relative acidity of each of those 4 liquids. Okay, so we've made it to part 8, which is testing for ammonia or ammonium ion. And for that, we're going to use some common household ammonia. And this bottle looks like it's vintage 1960s. It's really not ammonia, it's really an aqueous solution containing ammonia gas. So NH3AQ, similar to the ammonia solution on your bench tops. And what I'm going to do is pour out a little bit of this ammonia solution into this 150 ml beaker, about 5 milliliters or so. And if you're familiar with ammonia, it's got a pretty nasty smell. Lovely. And what we're going to do is we're going to take a piece of red litmus paper. And again, litmus is another chemical that indicates the presence of an acid or a base. We're going to use the red litmus paper, which is designed to pick up the presence of base if it changes color. And so what I'm going to do is I'm going to moisten the litmus paper first with a little deionized water. And then I'm going to hold the litmus paper over the ammonia solution. And let's see what happens as I swirl it. So the only thing that's coming in contact with this litmus paper is any gas that might be coming out of this solution. And as you can see what's happened to the litmus paper, it has turned blue. That's your observation. And what is your conclusion about red litmus paper turning blue? And what does that tell you about the gas that was coming out of this ammonia solution? You can put that in your conclusions. So now on to number 3 of part 8. And what I have here is some fertilizer. This happens to be solid fertilizer as opposed to liquid fertilizer. And it's a special blend fertilizer for hibiscus and tropical plants. And one of the elements that fertilizers provide for plants is nitrogen. And the nitrogen can be found in several different chemical forms. Sometimes it's found in the form of ammonium salts. And we're going to test this fertilizer to see if it contains ammonium salts. So I'm going to take a small amount of this fertilizer, put some of that fertilizer in the bottom of that beaker, and then to that fertilizer I'm going to add about a milliliter of approximately 20 drops of 6 molar sodium hydroxide. Okay, and now what I'm going to do is take another piece of red litmus paper, moisten it with water, and then hold it over the top of the beaker as I swirl it to see if it will turn blue. And sometimes this takes a little bit of time, but if there is ammonium salts in the fertilizer, the sodium hydroxide, being a base, will convert them into ammonia, and that ammonia gas will escape from the beaker and turn the litmus paper, the red litmus paper, to blue. And what do we observe happening? Turn to blue. So that's your observation, and what conclusion do you draw from that? Okay, so that brings that experiment to a close. Hope you enjoyed the reactions. And now It'll be up to your instructor to let you know how to prepare your lab report. Thank you. I'd like to acknowledge the help of my daughter Ruby Goodman in the editing of this videotape.